when I first discussed the idea of Hooke's law, if you remember, I drew a curve there, a curve of stress versus strain, and in that curve I said that there is a certain point up to which this ratio of stress divided by strain holds true. And whenever we define the Young's modulus or bulk modulus, even rigidity modulus, we always say this. Initially when we define those moduluses, we say that for a small strain. So what happens when the strain is not small? And that is what we will be addressing here. So if you look at this curve, this is also a strain versus strain, stress versus strain curve, but in this case the small strain which we were talking of is only up to point A, and from A onwards the strain is increasing. That means it is no longer within the realm of small strain. Now what happens up to A? Up to this point A, stress divided by strain, this ratio, the slope of the graph, if you may say, remains constant. That means if the ratio of stress to strain has a certain value at this point, the value of stress to strain is the same at this point, the same at this point, the same at this point, and so on up to A. So up to A we say it is where the Hooke's law holds properly. For small strain, ratio of stress to strain is a straight line, and that straight line is O to A. But what happens when we increase the strain even further? That is when we move from A to B. When we move from A to B, that is we basically increase the strain even further. In that case, as you can see, there is a curvature in the graph, which means that for a small increase in the stress, the increase in strain is greater, which means the increase in stress and strain are no longer in parity. They are out of parity now. For a small increase in stress, strain is increasing much longer. But even then, it remains elastic, by which I mean that if I am applying a force, say this graph is for a wear. Now if I am applying a force on the wear and I remove that force, then it will again retrace its path and come back to the origin, which basically means that it is still within the elastic limit. It will regain or retain its original dimension or length. So up to the point B, we say that this is the elastic limit or limit of elasticity. That is, up to this point the wear or the material is within the elastic regime. From B to E, this region is no longer the elastic regime, but it is the plastic regime, which basically means, like, if I again keep on increasing the force, that means the value of stress has now crossed the point B, it is somewhat more, and if I keep on increasing the stress even at this point, what happens is there is a permanent deformation in the length of the wear. That means if I keep on increasing the stress and the value of stress, suppose it reaches the point C, that is the amount of stress which has been developed within the wear, then if the external force is removed and the stress again becomes 0, the strain does not become 0. The strain becomes OC dash. It comes down along this straight line. That means there is a permanent deformation in the wear. There will be a permanent increase in its length. And that basically means that it is no longer within the elastic limit. It is not coming back or regaining its original dimensions. If we keep on further increasing the stress, say it moves from the point C to point D now. Now here the point D, as you can see, it is the highest point of the curve. This is the point corresponding to the maximum stress. When this is the amount of stress which we apply to a wear, the wear no longer remains a solid anymore, rather it behaves like a fluid, it flows like a viscous fluid. And then finally at the point D, what happens is the wear snaps. That means if this is a wear and a load is being applied at this point, when the stress reaches the point D, that is the maximum load this can take, forget about elasticity. Now what will happen is somewhere in the middle, the wear material of the wear will start flowing like a viscous fluid. They will get detached, and then the wear will tear off or snap at the point E. This point D, the stress corresponding to the point D is called the breaking stress. This is the maximum amount of stress which the material of the wear can take. And based on this graph, materials can be classified into two types: ductile material and brittle material. What are ductile materials? We know ductile materials are those, for example, like aluminium, silver, with which we can easily draw them into wears. And brittle materials are those which easily break. For example, dry clay balls. Then you can take, for example, glass. These are brittle materials. They can easily break down. Whereas ductile materials are those which we can easily draw into wears. Now, if you draw the stress versus strain curve for ductile and brittle materials, you will find that for brittle material, this point E is pretty close to the point B. That is, E is somewhere here, which means these brittle materials have got very small plastic region. As soon as their elastic region or limit of elasticity is crossed, if you apply more force than that, which means if more than that stress as corresponding to point E is generated within the material, it will break apart. That's brittle. So brittle particles have very small plastic region, whereas ductile materials are those for which these plastic region and elastic region, they are sufficiently larger as compared to the brittle materials. Now we will calculate the potential energy. We will calculate the potential energy in a stretched wire. Potential energy in a stretched wire. So this is quite obvious. Like when I am stretching the wire, what am I doing at the atomic level? So if you picture it like this, that say this is length of the wire, and this is an area of cross section. If I, at this area of cross section, if I magnify it, suppose these are my atoms. Say for example, these are my atoms, and when I am stretching it, what am I doing? I am increasing the lengths between the atoms. So the length is getting increased. This is what is happening when I am stretching it. Now these atoms, they have got a potential energy with respect to each other by virtue of their position. Where they are present within the lattice determines what is their potential energy. So with respect to each other, when the distance increases, their potential energy also increases or decreases, and so on. So when we are trying to stretch, we are doing some work on the wire, and where is that work going on? That work is going and manifesting itself as stored potential energy within the material. Now we will be finding an expression for this stored potential energy. Now we know this, that if we take a wire and we consider longitudinal stress and longitudinal strain, then Young's modulus is force by area divided by strain, and that turns out to be F by A, L by small l. This is Young's modulus. If I make force to be the subject, then force is equal to Young's modulus into area into longitudinal strain divided by the original or initial length of the wire. Now say this is the force which is being applied on the wire. So this is the wire, and this is the amount of force getting applied on it. And say by virtue of this application, the length of the wire increases by a very small amount dl. A very small amount dl. Then how much work I have to do in order to increase the length by dl? I will have to do a small amount of work dW, which will be force dot product with this dl. This is the amount of work I will have to do in order to increase the length by dl amount. So that will be equal to, this will be the expression for dW, and this is the amount of work which I need to do in order to increase the length by dl. And what is the amount of work I have to do to increase the length all the way by the amount small l? That will be work W, which will be integration of dW, that is integration of YAL by LDL from 0 to the final extension. Now this Young's modulus, the area and the original length are constants, so they come out of integration. This becomes LDL, so it's basically YA by L square by 2, so that is half into Young's modulus into area into L square by L. Now what I will do here is I will multiply top and bottom by another L, so that will become L square into L. Now I will rearrange this as half into Y into L by capital L within one bracket, A into capital L within one bracket, L by capital L another bracket. So I broke down this L square by L square. And here I multiply top and bottom by L. Now what is this thing? If you look, this thing is half into Y into small l by capital L from this formula is my stress. Small l by capital L is strain, and area of cross section into total length is volume. So therefore, what is the amount of work which we are doing in order to increase the length of the wear? The amount of work is equal to half into stress into strain into volume, and this work is getting stored as potential energy within the material. And therefore, if you want to find out the work per unit volume of the material, it is simply half into stress into strain. This is a derivation which is pretty simple, and often it comes in the exams, so practice this properly. That brings us to another topic, which is known as Poisson's ratio. Now, what is this Poisson's ratio? I do not know that if this question has come in your mind by now, but throughout the previous classes, whenever we talked about expansion in length during Young's modulus or during other moduli of rigidity and bulk modulus, we always said that this is the initial length of the wear, and applying the force, this becomes the new length. But you must have thought one thing, that the volume has to remain conserved. So if there is an increase in length, there must be a decrease somewhere. Otherwise the volume won't remain conserved. And when we think about this in detail, that brings us to Poisson's ratio. So if this is the wear, which is initially having say a diameter d, and it is initially having a length L, then I am applying a force in this direction and trying to increase the length of the wear. So now I successfully do increase the length of the wear by an amount, say L dash. Then there will be a decrease in its diameter as well, and the new diameter will be d dash. Because if you look into it like this, the initial volume is equal to area of cross section into length, so it is pi into diameter square by 4 into the length, and the final volume, that is pi into the new diameter square by 4 into the new length. Now obviously, if I consider that the diameter remains the same as we were considering all this while, that is if d and d dash, they are not different, d remains the same, you see this quantity is same, only L increases to L plus L dash, then obviously volume is increasing, but that cannot happen. So the length that is increasing is actually happening at the expense of the diameter, which is decreasing. So when there will be an increase in length, there will be a decrease in diameter, and when there will be an increase in diameter, there will be a decrease in length. So they are related with each other from the conservation of volume principle. And this brings us to what we said as the Poisson's ratio. Poisson's ratio, denoted by this letter sigma, is equal to minus d by capital D divided by L by capital M. So this small d here, that is not my d. The small d here is basically the change in diameter, and capital D is the original diameter, and small l is the change in length, capital L is the original length. So Poisson's ratio is defined as ratio of lateral strain to longitudinal strain. What is the strain in the lateral direction as compared to what is the strain in the longitudinal direction? This is known as the Poisson's ratio. And as you can see, these are all ratio of same quantities, so they have got no unit of dimensions. So sigma itself is a dimensionless quantity, and its value ranges from -1 to half. This is theoretically how its value ranges, but practically it lies between 0 to 0.5. So Poisson's ratio comes from the principle of the conservation of volume.